Okay, I stand between everyone and happy hour, so I'll try to make this somewhat brief. So I'm Megan Skinner, water quality specialist with U.S. Fish and Wildlife Service in Klamath Falls. And my role in our office is to better understand and improve water quality in the Upper Klamath Basin in support of recovery of two critically endangered fish species, lost river and short-nosed sucker. So today I'm going to be talking about cyanotoxins in Upper Klamath Lake, specifically monitoring that really started in 2016, and some expanded monitoring efforts in the last couple years. Okay, I think most people here in the room know where Upper Klamath Lake is and what it looks like. The key point here, again, is that the lake is home to two critically endangered fish species, Twam and Koptu, lost river, and short-nosed sucker. And several other species of conservation, cultural, and/or economic importance. Hopefully salmon in the near future, if not already. So we observe each summer large cyanobacterial blooms in the lake. These create problematic water quality conditions for our native fish and wildlife, odor and aesthetic issues, and often result in recreational advisories based on the toxin microcystin. These two graphs are just indicative of some of the water quality challenges for pH. Peak pH during the, or maximum pH, I should say, during the peak bloom period can be relatively high. And we also tend to see relatively large diel swings in pH. Relative to dissolved oxygen during the bloom crash period, we can see near anoxic conditions. I'll also note that within the cyanobacterial bloom, the primary species is Aphanizomenon flos-aquae, or AFA. This is the primary by biovolume. It does not produce toxin in Upper Klamath Lake. Second most common by biovolume is Microcystis aeruginosa. This is a producer of microcystin. Other noteworthy species or taxa in the bloom include Dolichospermum, Pseudoanabina, and Gliotrichia. Though they tend to occur in biovolumes orders of magnitude less than AFA and Microcystis aeruginosa. So in terms of cyanotoxin monitoring, the first quantification was microcystin in 1996 in Upper Klamath Lake. And routine monitoring for microcystin really began in 2016 by the Department of Environmental Quality in the state of Oregon. These are surface grab samples collected twice monthly, typically May through October or November at 3 sites. And I'll also note that a Fish and Wildlife Service effort in 2021 detected microcystin, cylindrospermopsin, saxitoxin, and anatoxin-a in nearby water bodies. These were refuges in California that receive water from Upper Klamath Lake. So these observations in 2021, combined with the knowledge that taxa capable of producing multiple toxins exist in the bloom, led us to believe we may need to expand our monitoring efforts, which we began exploring in 2022. So before we get into the expanded monitoring efforts, I just want to illustrate our period of record that we had access to prior to that expanded monitoring in 2022. Note that the Y scale is in, or the Y axis is in log scale. The 3 different colors represent the 3 different sites. The red line is the Oregon Health Authority's advisory criteria for microcystin, which is 8 micrograms per liter. And the story here is that microcystins were regularly detected in the lake and often at levels well in excess of the OHA advisory criteria. So starting our expanded monitoring effort in 2022, this included DEQ standard monitoring, collection of water grab samples, tested for microcystin, collected twice monthly at the 3 sites you see there on the bottom right. And I'll just note these focus on recreational areas on the south and west side of the lake, and collected May through November. In 2022, this was paired with Fish and Wildlife Service, also collecting water samples, tested for anatoxin-a, cylindrospermopsin, microcystin, and saxitoxin. These were collected once monthly, May through September, at the same 3 sites. And I'll just note these were collected less frequently due to the cost associated with ELISA analysis for all 4 toxins and funding constraints. with the exception of May. These were all collected in the first half of the month, concurrent with the DEQ effort. So we'll add a year to our period of record, and we can see that generally microcystin concentrations were lower in 2022, but we did have a couple outliers that exceeded the advisory criteria, so there was a recreational advisory. And these again are the DEQ water samples. Now, unfortunately, the first half of the month just happened to correspond, each month just happened to correspond to dates in which microcystin concentrations were really low. This was really unusual for the bloom in Upper Klamath Lake because typically we could expect microcystin concentrations in excess of that OHA advisory criteria on any sample date. So this was a little unlucky for our study, but of course it is indicative of the discrete nature of grab samples and the fact that they may miss those spikes in concentrations. Note here as well, we had non-detect for anatoxin-a, cylindrospermopsin, and saxitoxin on all sample dates. So the cost associated with collecting water samples frequently enough and testing those for all 4 toxins led Fish and Wildlife Service to consider alternative methods for 2023. So in 2023, DEQ once again implemented their standard monitoring, which is collection of water samples tested for microcystin twice monthly, May through September at the 3 standard sites. Fish and Wildlife Service paired this with SPATT samplers deployed weekly, tested for all 4 toxins in the months of August and September at the same 3 sites. I would normally take a detour here and talk about SPATT, but Mike just did a great job of that. I will just emphasize once again that SPATT samplers are detecting dissolved toxins, whereas water samples are typically detecting total toxins, which would be dissolved and particulate, or those bound in cells. Okay, so let's add another year to our period of record. 2023 looks a little bit more normal for this period of record. We had a number of samples that exceed the OHA advisory criteria. And again, these are DEQ water samples. So now we're going to compare water and SPATT. So on the left, we have microcystin concentrations in nanograms per gram. This corresponds to Fish and Wildlife Service SPATT samples in the bars on the graph. On the right, we have microcystin concentration in micrograms per liter. This corresponds to DEQ's water samples in the lines on the graph. So in many ways, 2023 was a proof of concept. I wanted to determine if I was able to detect a microcystin in the SPATT samplers when it was detected in water samples. And the answer to that question was yes. We never had a date in which we had a SPATT sampler deployed and we had microcystins detected in water that we didn't also see that in the SPATT samplers. In terms of trends between or comparison between the water samples and the SPATT samples, there aren't any clear patterns here. And in fact, when we had some of the highest microcystin concentrations in water samples, we saw the lowest concentrations in our SPATT samples. And there's a couple of reasons why this may be. Again, SPATT samplers are only detecting dissolved toxins, so they may not pick up those high concentrations associated with scums, which is what we're typically targeting with water grab samples. Conversely, because SPATT samples are a time-integrated passive sampling method, they may pick up fleeting peaks or spikes in concentrations that water grab samples may miss. So looking at our anatoxin-a results, recall we don't have water samples in 2023 for anatoxin-a, which in hindsight is a little unfortunate since we did have more toxin production generally that year. But the punchline here is that this represents the first consistent detection of anatoxin-a in Upper Klamath Lake. I will note that the concentrations in nanograms per gram are relatively low. What you just saw from Mike's talk is that they often observe concentrations in hundreds of nanograms per gram, but this is the first time that we're seeing this. Okay, so moving on to 2024 or this year. So based on the facts that we routinely detected anatoxin-A in 2023, we decided it made sense to pair testing for that toxin in both water samples and our SPATT samples. So DEQ this year was collecting water samples, tested for all 4 toxins, collected twice monthly, May through September, at the standard 3 sites. Fish and Wildlife Service paired this with SPATT samplers, also tested for all 4 toxins, deployed twice monthly as well, July through September at the same 3 sites. And the idea with deployment timing here is that the SPATT samplers were deployed 7 days prior to water sample collection, such that the results from the SPATT samples representing the 7 days up to and including that grab sample collection. So we're going to add the final year to our period of record, and there's been some hints already today, but it was a really weird year. No water samples collected by DEQ had concentrations exceeding the OHA criteria, advisory criteria for microcystin. This is the first time we've observed this in the period of record for water monitoring, and it's also the first time this has happened since I've lived in the basin. And in case you don't believe me, I'll just show here, this is pH. We use this as a proxy for primary productivity. You can see that peak pH this year was lower than what we've seen in any other year in the period of record for our routine microcystin monitoring. So does suggest both less production, toxin production in the bloom, and also a smaller bloom overall. So now comparing our water samples and our SPATT samples, this is microcystin again. On the left, nanograms per gram for SPATT samplers and the bars on the graph. On the right, micrograms per liter for water samples and lines. In terms of water samples, you can see, yes, we're well below the OHA advisory criteria. Interestingly, in our SPATT samples, we had higher toxin concentrations this year than we did in past years. And this again may be an indication of the discrete nature of water samples. This is a picture at the UKHP site, which is at a boat launch off of Highway 140. I took this picture on July 5th when I deployed a SPATT sampler. When I came to retrieve it on the day of the water sample collection, the bloom had subsided substantially. And so this is just an example of potentially what a SPATT sample is collecting versus a water sample that may have missed this entirely. And then we'll look at anatoxin-A. So recall, we do have water samples for this year. Note the red line, that's 15 micrograms per liter. That's the Oregon Health Authority's advisory criteria for anatoxin-A. Again, nanograms and bars for SPATT samples, micrograms and lines for water samples. We did not detect anatoxin-A in any of the water samples that DEQ collected this year. And we did detect anatoxin-A in our SPATT samples, but far less frequently and at lower concentrations than in 2023. So in conclusion, we observe large cyanobacterial blooms each summer in Upper Klamath Lake. These include taxa capable of producing a variety of cyanotoxins, though of course we've seen some recent variability. Microcystin and anatoxin-A are both present in Upper Klamath Lake. Microcystin is routinely detected in water samples and SPATT samples, and anatoxin-A was routinely detected in SPATT samples in 2023. We had some detections this year, but we never detected it in water samples in Upper Klamath Lake. Anatoxin-A is likely present in concentrations too low for detection in water samples, or grab samples may be missing those measurable spikes. And I'll have some recommendations in a minute on how we might approach this in the future. Cylindrospermopsin and saxitoxin were never detected in water or SPATT samples in our expanded effort from 2022 to 2024. Again, despite fairly routine detections of both toxins in nearby water bodies that do receive water from Upper Klamath Lake. So that was a little bit of a surprise. So potential next steps, don't necessarily have funding in place for these, but just some ideas to consider for future years. First, DEQ is likely to continue their routine microcystin sampling in future years. It's unclear what additional toxins may be included in that effort. For anatoxin-a, I propose considering what I'll call the California model, which is a modification of the tiered approach that Mike just presented. Note that the tiered approach, of course, corresponds to riverine systems and benthic blooms, but I think there may be some applicability for Upper Klamath Lake. So first, I suggest we use SPATT samplers as sentinels for an increase in toxin production. We would follow that with routine water samples once SPATT toxin concentrations are in the 10s to 100s of nanograms per gram. You'll recall that we were typically around 1 to 4 nanograms per gram in our samples in 23 and 24. And we'd focus our SPATT monitoring in late July and through September, given the findings. So I have a number of folks to acknowledge for their assistance in this work, and I tried to make it fast, so we might have some time for questions if folks have any. Mm-hmm.
Definitely have time for questions. Laurel has one.
Megan, do you guys have, are you still collecting any algal samples for taxonomy and just starting to think about like the taxa that are potentially producing the toxins? And also thinking about, I know it's often very turbid, but thinking about the potential for benthic scums just on the very edge of the lake, given that that might really change the way you try to sample for some of these toxins.
Yeah, absolutely. So, you know, to my knowledge, there hasn't been or structured monitoring for benthic cyanobacteria in Upper Klamath Lake. The fact that we are detecting anatoxin-a makes me immediately suspicious that we may have a benthic, particularly given your work, Laurel, in the river. You know, benthic cyanobacteria is not something I have much experience with, so this is something I'm going to be thinking about and exploring over the winter, and I'll certainly be talking to you, Laurel. I will say that the water samples that Fish and Wildlife Service collected in 2022, we did also have taxa ID done on those. And it was primarily Dolichospermum and Gliotrichia. Didn't catch any wisps of benthic cyanobacteria there. Yeah.
So I work on the Trinity River, so forgive my ignorance of how Klamath Lake functions, but are there any, is there any knowledge or hypotheses on the presence of cyanobacteria in upper basin lakes historically or prior to Eurocolonization?
Sure, yeah, so I think at a past KBMP, I may have given a talk about the story of Upper Klamath Lake, because it's a good question and it is an interesting story. So AFA, the Aphanizomenon, aconites show up in the sediment records in the early 1900s, but they really weren't present prior to that. You know, the algal communities evident in those sediment cores prior to that were really consistent with eutrophic, not hypereutrophic, which is what we are now, but a eutrophic lake wetland complex. So there was a shift in the community. The first reports of cyanobacteria, AFA specifically, I believe we're in the 1930s, and you know, by the 60s and 70s is described as a monoculture. So you know, it really picked up during the 20th century. And phosphorus really is the key driver for these blooms. It's what feeds them. And so the TMDL for Upper Klamath Lake, which has been subsequently supported with additional modeling, indicates that decreasing the external phosphorus load to the lake will control the blooms. So we know what to do. It's just an immense challenge to get that phosphorus under control. So, yeah, Desiree.
Hey, Megan, great talk. Thank you for the summary. I'm curious if you have any ideas about what happened this summer, because we're facing the same sort of mystery in the Cascade Lakes to the north and Ross Island Lagoon, like expected a big bloom year and nothing materialized. And so I'm curious if you have any sense if there's this regional thing going on, if there was something unique to Upper Klamath Lake. Do you have any thoughts?
Yeah, so I have a few theories. First, we had relatively low inflows to the lake this winter, despite average to above average snowpack. And our phosphorus load, though we're seeing statistically significant decreases in concentration of phosphorus in our inflows, load is still largely driven by volume of water. So you have lower inflows in the winter, you're likely to have less phosphorus load entering the lake. So I think that was part of it. We also, and I'll just say this is all preliminary and some of it's anecdotal, haven't had a chance to dig into anything yet, but I'll also just note that we seem to have a really windy late spring, early summer. We also, water surface elevations in Upper Klamath Lake were a little elevated this spring relative to what we'd seen in past years. And so I think a combination of those factors may have delayed onset. In July, just as the peak was, just as the bloom was peaking, smoke rolled in. So I think that cut the top off the bloom, and it just didn't fully rebound after that. We had smoke off and on for most of the month of July and some of August as well. So those are my theories. Oh, and I will also add, just anecdotally, it seemed like there were observations of much more submerged aquatic vegetation in the lake this year. So there may have also been a cycling of phosphorus away from cyanobacterial, the cyanobacterial blooms.
Any other questions for Megan? Randy?
Thanks, Megan. You mentioned the saxitoxin and cylindrospermopsin in the refuge, but not upstream in the lake itself. Have you considered deploying SPATs in the irrigation canals to see if that potentially is a source?
I haven't considered that, but partly because I personally am kind of maxed on capacity. You know, I will say, you know, SPAT samplers are great because they're passive, they're time integrated, but you still do need to go out to each site once a week. And depending on how far that is from your office, like once you're at your site, you're pounding rebar in the ground and you're attaching a sampler with zip ties. So, you know, that takes 3 minutes, but you know, it's traveling to your sample site. So it's a good idea. If we have capacity and interest to implement something like that, I think it'd be really interesting. I'll also note that water management has changed substantially in those two refuges in the last 2 years. And I have not seen cylindrospermopsin since. I have seen very, very low, like barely detectable concentrations of saxitoxin, but yeah, some of those things have changed.
Thanks, Megan.
Yeah.
Thank you.